Hey guys, this lesson is on reviewing graphing functions, their transformations, and their behavior. This is a lesson I typically do at the beginning of pre-cal. It can be watched during any course, whenever you just need a refresher, but it's a great head start. You will see a lot of the way we label things and move things around in calculus as well. So this worksheet and the next few that I'm going to show you, you can find on my website in case you want to print it out. That website is Mrs. MRS Del Valle, DELVALLE 1218.com. And it should be under the resource file and you'll see the graphing worksheet. All right. So let's get started. The first thing we're going to do is just remember what the parent functions look like. Okay. You're going to hear me say some silly references. If you like my silly reference, write it down. If you can come up with your own, write it down. It's the type of things that's going to help you memorize what they look like, and then we'll just see how they move around. So this first one that we have is a linear function. The most important thing to remember here is that the exponent is a 1. Remember, we don't see the exponent when it's a 1. So whenever you have a function that is x to the first power, that is when we have a linear function. And we'll go over all of this on the next worksheet, okay? So you could see the linear function. This is the parent function, so it's centered at the origin. We haven't moved it yet. And in class, I call this disco fever. I'll literally have you stand and put your hands up like John Travolta in disco fever, okay? Now for this next one over here, we have the brackets, or not brackets, the two lines, which is the absolute value. Okay, so in class, I would have you put your hands up like a goalpost, right? And then I'd have you just open them up to make a V. So the two lines is the goalpost, right? And then you open it up, it's a V, that's the graph. Okay, and again, it's just a parent function, so it's just centered at the origin. All right, so we go on to the next one, y equals x squared. This is a quadratic. Okay, and it kind of looks like a U. So if you know me, you know I am a UM fan. So I tell everyone, x to the U, it's all about the U. Okay, so here's like one of the things I would do in class to help you remember. All right, x to the 2, it's all about the U. Okay. So again, anytime you see an x squared, you're drawing that U shape, and then you're just going to move it around according to the transformations. Okay, and again, we'll go over all these details in a moment. So the next, we have, we're used to calling this a square root. And I'm going to have you not call it a square root for a moment, or a radical. This one specifically is for even roots. Okay, so not only square root, but a 4th root will also look like this. A 6th root will also look like this, and so on. Let me compare it really quick to the one underneath. You have a cube root. This isn't just for a cube root. This is for any sort of odd root. So 3rd root, 5th root, 7th root. Okay, so even roots, odd roots. Okay, even roots start at the origin and go over. Okay. Now, I'm going to skip this one for a moment because odd roots, like the cube root, for instance, has that same portion, but it also reflects down and has the same thing like a tail. Okay? So the square root or the even root only has the front half, and then the odd roots or the cube root has the tail end as well. Okay? And if we were in class, I'd tell you to put your hands one forward and one behind you, and you'd walk like an Egyptian, you know, like that song. All right? We'd be doing a lot of silly little dances. By the way, if you are into the silly dances, if you look on Google or Pinterest and you put function graph dances, you're going to see little stick figures doing all these dances that I'm talking about, okay? All right, so moving on, we had x squared was a U. And now x cubed, it's like the U, but one of the sides drops down. So in class, we would do the robot. Okay? So if you right now put one hand up and put the other hand down, you'd be doing the robot, dancing the robot. Okay? All right, let's move on. Now, I'm going to show you these next two briefly, but I'm not going to go into detail on these two because, again, this video is meant for my pre-calc class. When we hit chapter 3, we will go in depth on exponential and log, so I'm not going to take too much time on that now. And it's hard to see it here anyways. Exponential functions is when you have the x in the exponent. And it's hard to see here, but this continues on all the way. And it approaches an asymptote. Okay, so here on the x-axis, there is an asymptote going on. And that's where that orange line continues going all the way through. Okay? For logarithmic function, the same thing happens, but towards the side. We have this asymptote going on here, all the way down. Okay? And then the function, it kind of almost looks like this one when you put it, in your graphing calculator, but it continues going all the way down through the asymptote. Okay? Remember, we approach asymptotes, but we do not ever touch them. Okay? Now, these next two that I'm going to show you are very important. They have two asymptotes. These are rational functions. You should have done a big chapter on this in Algebra 2. These are definitely some of the trickier ones to graph. So I'm going to draw you the asymptotes on both of them, and then I'll show you the differences. So both of them have an asymptote on the x-axis and the y-axis, okay? So here we have the x-axis and the y-axis, okay? All right, and now the difference between these two is the exponent in the denominator. So these are rational functions. When I teach Algebra 2 or trigonometry that we go over this, in parentheses down here with rational functions, I would put the word fraction functions. Okay, rational functions is a fraction function, okay? And then the same thing here. So anytime you have a fraction function, you want to determine whether the exponent on that x is even or odd. So here we have 1 over x to the first. Okay, so x raised to an odd number. So they are on opposite corners. Okay. There you go. So you have 1 there and you have 1 over here. Again, we approach those asymptotes, but we do not touch it. Okay, so now when I have 1 over x raised to an even number, 1 over x squared, then both of them, think when things are even, they're symmetrical. They're both up top. Okay, and if it was negative 1 over x squared, then they'd just both be on bottom. Okay, sound good? All right, down here we have what's called the greatest integer function. It's also sometimes known as a step function. We're not going to go in depth on that. I don't even think you've ever really, it comes up in AP Cal. So I don't want you to stress on that. Just know that these brackets around an x, it just exists on the whole integers, the entire integer. So here it exists from 1 all the way to 1.9999, and then it's hard to see, but there's an open circle there. If you Google it, you'll see a better image, but again, don't stress about this one. And the last one is probably the easiest, most common, y equals c, where c is a constant. Okay, you can see the word constant right here. So that's like if it was y equals 2, you would just draw a line at 2. All right, this is just old school. Not too concerned about this one. All right, so now let's go ahead and, now that we've seen what these graphs look like, let's go over and take a look at what a transformation of these parent functions would look like. Alrighty, so here, it's kind of a general, this is another worksheet, this is the back side of that worksheet, of what the transformations look like. I want you to take a minute and put a plus or minus in front of all of these a's. Okay. Now the plus or minus determines whether the function would flip up or down. Okay, so if it's positive, it stays facing upward. And if it is negative, it flips downward. Okay. The A, and I'm going to show you these notes in a moment, so I know I'm going to talk fast, but then I'm going to put all the notes that I'm saying on the screen. The A is being multiplied, so that's going to stretch or shrink the function. A, if it's negative, ignore the negative and just take the negative as it flipping it downward. I want you to think of A as either a fraction, less than 1, or a number greater than 1. So I always like to think of a bank account because money makes sense to me. So if I multiply the number 2 to my bank account, what's going to happen to my bank account? It's going to grow, right? And then if this A was a 1/2, if I multiply 1/2 to my bank account, then my bank account is going to shrink. And then the last scenario is if A, technically if A was 1, you wouldn't see it there because when we multiply something by 1, we don't really put that number 1 there. But if I multiply my bank account by 1, then it stays the same, okay? It does not stretch or shrink. Notice that H is always inside of the parentheses, or for example here, it's the bars for the absolute value. So I would say inside the grouping, okay? Even as we go down here, it is grouped in the denominator, okay? H is going to move the graph, the image, side to side, opposite of the sign. So anytime you see a number, H is going to be a number, inside of the grouping, it is going to move side to side, opposite of that sign. So if it says -3, you're going to move it 3 to the right. Okay? And now K, notice, is always on the outside of the parentheses or outside of the grouping. That's going to move the image or the function up and down, same as the sign. Okay? So let's take a moment and look at what those notes look like. Okay? So you can pause the video and write this down. Okay, so one more time, we said the plus or minus is going to flip the function. If it's on the outside, which is what we just saw in that image, on that last worksheet, I'm sorry, it's going to flip it up and down. Okay, now if it's on the inside, it's going to flip it side to side. So an example of that here is the square root. So if it's just square root positive, it goes like in the image we just drew. If I have a negative on the outside, it's going to flip it downward. If I have a negative on the inside, right, the inside is going to flip it to the left. And if I happen to have both, it's going to flip it down and to the left, okay? Now, we said that A was a stretch or shrink, depending on whether A was greater than 1 or a fraction less than 1. But greater than 0, because remember, the negative will just determine if I flip, okay? Now, be careful for the common trick here, is if A is a fraction like 5/2. So 5/2 is a fraction, but remember 5/2 is greater than 1. So be careful, that would really be a stretch. Okay? H shifts it side to side, opposite the sign, and it'll be inside parentheses. K shifts it up and down, same as the sign, and that will be outside of the parentheses. Oh, got to close it. All right? Now, after we graph, I'm going to ask you a few things, okay? I'm going to be asking you for the domain, range, when it's increasing and decreasing, and what the max and min is, okay? So the way we list that, the domain is where the function exists, and the way we label it is we'll list the furthest x to the left, we'll put a comma, and then the furthest x to the right, and we'll put the parentheses on the outside, okay? We'll put brackets, and I'll reiterate that down here, if it touches an actual location, okay? Range is the same thing, but where it exists up and down. So we'll put the lowest y value that it exists at, and then the highest y value that it exists at, okay? Again, with either parentheses or brackets, depending on what the scenario is, okay? Increasing and decreasing, we're just literally checking from left to right, okay, from left to right, when the function goes upward and downward. And we will list those in separate parentheses in the same exact way that we list domain. All right? For our max and our min, you can do one of two things. You can just put the y value, or to play it safe, you can put the ordered pair. The reason why I say play it safe is because if you list the x value, that is not telling you what the actual value of the minimum or maximum is. It's telling you the location of it. So be careful with that. So now, when to know when parentheses and brackets are used. Parentheses are used when we are talking that the function goes off to infinity, okay? or that it approaches somewhere and doesn't touch it, which we said that happens with asymptotes, okay? Or if you have an open circle. We won't see much of that today, but that does happen at times, okay? Brackets are used when we touch an actual number or a closed circle, okay? So we are going to see examples of all of this in just a moment. Now, whenever I want to imply an infinity, I'll draw an arrow on my graph, okay? So if you notice with that orange highlighter, I drew arrows at the end of each image. That indicated that the function went on forever into infinity, which we said infinities would get parentheses when I'm talking about them. If all of this seems like a little much, pause the video, write the notes down, and I'm going to do an example of each of the parent functions we just talked about, okay? So let's start simple, okay? I'm going to get a different color pen here so it's easy for you to see. Okay, so y equals -4. If it's just a number, this is a constant. Okay, now when I give you homework, quiz, tests on graphing, what I do here is what I'll expect from you in order to get full credit. Now, mind you, when I teach this, I teach with the thought of preparing you for AP Calculus. So it's also what is expected from like an AP Calculus test. Okay, so don't think you'll have to relearn something. Okay, so as long as you draw your graph, 1, 2, 3, 4, you indicate that this is -4. Then you just draw your function going off in both directions. There's your constant. Okay, domain. How far left does this exist? It exists all the way to -infinity. And then how far right does this exist? Well, that arrow indicates to the right is +infinity. Just realized I forgot to mention something over here. In case you're still confused with infinities, okay, going up or to the right indicates positive infinities, and going down or left indicates negative infinities. Okay, think of a number line. The further to the right I go, the bigger the number gets, and the further to the left I go, the smaller a number gets. All right, so, and infinities get parentheses. Range, what is the lowest this goes, and what is the highest? Well, constant functions only exist at that one number. So this is the only scenario that for our range only exists at -4. Okay? Now, for increasing and decreasing, I want you to put your pencil, I'm working in pen for the sake of the video, at the furthest left point of the graph. And as you move your pen towards the right, ask yourself, am I going up, down, or am I going straight? Well, this function is a constant. I'm always going straight. So I am neither increasing nor decreasing. Okay, so you could just put a slash, or you could put none or NA, not applicable. And then, does this have a maximum or a minimum? Maximums should look like mountaintops, and minimums should look like valley lows, okay? This just goes straight, so I don't have those either. Okay, we will see these in the upcoming images and graphs. For our next one, okay, we have 3x plus 5. What is the exponent on the x? There is none there, so you can assume it's x to the first power, which means that this is a linear function. A linear function looks just like this. I like to give myself a little reminder. Okay? Now, that 3 in front of the x means that it's going to stretch by 3. Now, whenever the function is a straight line, you can assume that that stretch or shrink is your slope, your rise over run. Okay? Once you have a function that curves instead of goes straight, it is no longer treated as a rise over run. Okay, that is what you will start to learn in calculus, of how rates change when they're not always going 3 over 1, 3 over 1. Okay, and this also is going to go 5 up. Okay, so I'm going to draw my tallies. 1, 2, 3, 4, 5. Okay, and because this is linear, I can treat 3 as a rise over run. So 1, 2, 3. And 1, and then you just draw your linear function. All right, so domain for this left, this always will shoot out to the left, and this will always shoot out to the right, okay? There's no breaks happening. When there are no breaks, you can assume that it is always negative infinity to positive infinity. Range, according to this arrow, the lowest it'll ever go, it goes on forever, is negative infinity. And then the highest that it goes is positive infinity. Now, for increase and decrease, if I put my pencil or pen furthest to the left and I start moving it, I see that I am always increasing and I never switch to decreasing. So I'm never decreasing, and the word always indicates negative infinity to positive infinity. So I am always increasing. Now, a linear function does not make a peak like a mountaintop or a valley, so I have no max or min. Okay? I know these seem a little too easy. We're going to kick it up a notch. Okay? So I see the absolute value bars. So I know that this is going to be like a V. Okay? Now that negative means that I'm going to flip. It's on the outside, so I'm going to flip down, which means it's not going to look like a V facing downward. That -3 is inside the grouping, so that's my H. So it's going to move 3 side to side, opposite the sign. So since it's negative, it's going to go 3 to the right. And that -1 is on the outside, so it's going to go 1, same sign, down. So I'm going to go 1, 2, 3. And 1 down. Mark your numbers. Okay, I'm going to draw a dot, and then I'm going to draw my V facing downward. Okay. Now, when I look at your graphs, what I'm going to give you credit for, guys, is the location, the image. I'll check your stretch and shrink by this list of notes that you write, and then I'll check this chart. Okay. So domain. This function always goes left, never has a break, and always goes right. Okay, so again, that always word. Range. This graph always goes down. It does not always go up. If I look at where this function exists, it only exists up to this dot. Okay? So remember, range is lowest y, arrow means negative infinity, up to highest y. The highest y value is -1. Now, because this dot is filled in, this -1 gets a bracket. Okay? Now, for increase and decrease, I'm going to put my pen furthest to the left. Now, arrow facing down and to the left indicates negative infinity. So from negative infinity, I start increasing up until 3. So negative infinity. Remember we said increasing and decreasing, if you look back at your notes, is the leftmost x to the rightmost x. So remember, these are my x's, these are my y's. So I went from negative infinity up until 3. There's a dot. I'm sorry, even though there's a dot is what I was going to say. I'm not going to put a bracket because technically at 3, I'm not increasing. So I'm at 3, stopping increasing and changing to decreasing. Okay, so 3 is going to be my maximum, 3, comma, -1. So that does not count as increasing, which is why I put parentheses. Now, from that 3 on forever, I decrease. Now, here I do have a maximum. I have a peak to my mountain. And you could either put your y value, which is -1, or you can put the ordered pair of 3, comma, -1. Okay? And ordered pairs always get parentheses. And there is no valley. There's no peak at the bottom, so there's no min. All right? Let's keep moving. One of the most common functions you probably saw in Algebra 2. Okay? I have an exponent of 2, which means that this is a quadratic. Okay? x to the 2, it's all about the u. Okay? It's positive in the front, so it's going to stay facing up. It stretches by 4. I have a +1 on the inside of the grouping, so it's going to go side to side, opposite the side. So it's going to move 1 to the left. And I have a +2 on the outside, so it's going to go up and down, same sign, so it's going to go 2 up. Okay? So I'm going to go 1, 2, and 1 to the left. I'm going to put my dot, and then it's positive, so my u is going to face upward. Again, don't worry about the stretch. As long as you list it here, you will get credit for that. Now, domain. This always exists all the way to the left and all the way to the right, because imagine these arrows shoot forever, always, always opening. Range. What is the lowest that you see this function existing? Okay, the lowest is right here. Okay, so this lowest is 2, and then the highest, the arrow, is infinity. So there's a circle filled in at that 2. I'm going to put my bracket, and it goes all the way up until infinity. Okay? So now increasing, I'm going to put increasing and decreasing. I'm going to put my pencil furthest to the left, and if I want to draw this, I have to start going down, 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 up until right here, which is, remember, for increasing and decreasing, I use my x's, -1. So use your hand to cover. From there to there, I decrease from negative infinity for this left to -1. I am decreasing. Remember, we do not put brackets on increasing and decreasing. And then from -1, I start to go upward, and that arrow means that it'll happen forever. So I go from -1 up until infinity. Do I have a maximum? Do I have a peak up top? Nope. Do I have a minimum? Yes, I do. Right here, this is the lowest, right? And that happens, again, either the y value at 2 or the ordered pair, which is -1, 2. Okay? Moving on. So we have a negative, and we have, we have this radical. If we do not see an index on this radical, meaning we don't see a number here, we can assume that this is a square root. So this is specifically an even root, which means that from the image, it shoots only to one side. Okay? This -2 on the inside, again, on the inside, is going to go 2 opposite the sign to the right. And this +1 on the outside means it's going to go 1 up. Okay? So now I'm going to go 2 to the right and 1 up. Draw my dot, and it doesn't, oh, I'm sorry, there is a negative. Look at that. So if we can just write it down here, the negative means that it's going to flip. It's on the outside, so it's going to flip down. Okay, so from this dot, we're just going to go down. Don't worry about how down you go. These are just sketches. These are not exact images, okay? So domain, furthest left that this graph exists, well, there's a solid dot here. There's not an arrow shooting forever. So the furthest left x that it exists at is 2. So we put a bracket as it touches it. It's a filled in circle. And then the furthest right, it goes on forever to positive infinity. Range, what is the lowest this goes? Well, this area is lower than this part. So the lowest it goes, there's an arrow, so negative infinity. And then the highest that this goes is up here to this dot. Okay, so the highest y value is at 1. And it's a closed dot, so I'm going to put the bracket. Okay. Now, this function, if I put my pencil furthest to the left for increase and decrease, always goes downward. So it always decreases. So it decreases. What's the furthest left that it starts at? Is 2. And then it decreases on to infinity. Max and min. Do I have a highest or lowest point? Okay. In case this was never Made clear to you, infinities do not count as maxes or mins. An infinity is a concept describing that the function goes on forever, not that it actually stops and makes some highest point or lowest point, okay? So make sure you don't include those infinities as max and mins. So there's no min, but there is a max up here. The y value is 1, or we can say the ordered pair of 2, 1. And we said there's no min. Okay? We're almost there, guys. We have 4 more examples left to go. Oops, let's zoom out a little bit. Alrighty. So if we look at this first one, we have y equals half x plus 3 cubed. So I see that cube. I know it's a cube function. This is my robot. So it's going to look something like this. Okay. That 1/2 means that it's going to shrink. Don't worry about drawing a shrink. As long as you write it here and understand it, you'll get credit. There's a plus 3 on the inside, so it's going to go 3 to the left, opposite the sign. And a minus 2 on the outside, so it's going to go 2 down. Okay? So 3 to the left, 1, 2, 3. And then 2 down. I'm going to go ahead and draw a dot there. Okay, it didn't flip, so I'm just going to draw my robot. We go up this way and down this way. Okay? And don't ever worry about your drawing skills. That will never be as bad as mine. Okay? So now, we have our domain. These arrows indicate that it always goes left, right? This will always go a little more left, a little more left. This will always go a little more right. We can also see that the same is true for range. This will always go down, and this will always go up without any breaks happening in between. So both of these are negative infinity to positive infinity. Now, if I put my pencil furthest to the left, and then I draw this function, it always goes up and it never decreases. So, never decreases and always goes up. Okay? Now, this function does not have a peak or a valley, right? So it doesn't turn around and go back down or anything of the sort. So there is no max and there is no min. All right? Moving on, we have a 3 in the index of this root. So this is an odd root. Odd roots, remember, they look like the square root, but they also have that tail end. So it goes over, but then it also goes under down this way. Okay? The negative means that it's going to flip. So instead, it's going to happen this way. All right? That 4/3, be careful, that is a number greater than 1. So although it's a fraction, this is a stretch. 4/3 is greater than 1. All right, that minus 1 on the inside, side to side, opposite the sign. So it's going to go 1 to the right. And that minus 3 on the outside means that it's going to go 3 down. You're probably going to get to the point where you don't need to write all these notes on the side, guys. But for now, go ahead and do so you don't miss on those little things, okay? So we're going to go 1 to the right, 1, 2, 3 down. So here's 1 and here's negative 3. And remember, it flipped, so it's going to go this way. We are not worrying about what that y-intercept is. We'd have to do a lot more work to figure that out, okay? So, domain, just like all these other ones, they're always going left and right, and this is always going up, and this is always going down for the range, okay? There's no break, so these will be negative to positive infinities. If I put my pencil furthest to the left and I start drawing, notice that my pencil always goes downward. So it is always decreasing. And I never turn around to start increasing. If it would have been the parent function, this one's always increasing and never decreasing. And notice that this doesn't make some sort of a mountain or a valley. There are no maxes and mins. This dot on both of these here In case you might be thinking it's a max or min, it's what it is a change in concavity. This is concave downward, and then it switches to being concave upward. Same here, it's concave down and then concave up. All right, which you'll learn a lot about that in calculus. All right, last two, we have our fraction functions, our rational functions. Okay, so we see a fraction, right? And the exponent up here is 1, so this is an odd, okay, fraction, which means it's going to be on opposite corners. Okay, now the negative means it's going to flip. The -1 grouped on the inside is going to go 1 to the right. And the +4 on the outside means it's going to go 4 up. Okay, now for these, that up and right are going to be your asymptotes. Okay, so notice in the parent function, I drew the asymptotes on the x and y axis. Now it's going to move 1 to the right. And 4 up. Okay, now initially I would draw it in these two corners, but because it flipped, I'm going to draw it in the opposite two corners. Okay. Now let's take our time here with the domain and range. Okay. So I exist always to the left, right? Domain is always existing to the left. Now as I keep drawing, I'm always existing, but the function does not exist at 1. It approaches 1. So keyword there is approaches. Since it approaches 1, I can put the 1, I just have to put parentheses. That means it's going to get really close to 1, but it's not going to touch it. Okay? Then I'm going to put union because it does exist. Union is like saying the word and, by the way, in case you don't remember that from Algebra 2. So I put the union to say it also exists after 1. So if this is 1, okay, it also exists from 1 approaching and then on forever to the right. The same exact thing is going to happen for range, but remember range is wise from bottom to top, so it's always going to exist from -infinity, but it's going to take a break and not exist at -4. It will approach it, right, and then keep existing on forever. So follow my finger, it'll go from -infinity up and approach this asymptote, which is at -4. And union, it'll also exist from -4 approaching it. If it touched -4, I would have put a bracket. And then it keeps existing up forever. All right? Now, if I put my pencil furthest to the left and I start drawing, I am increasing. Arrow indicates -infinity. And then I stop increasing at this asymptote, which exists at 1. Then, after 1, I put my pencil furthest to the left. There's a second part here. And I draw. And I am also increasing. I went up and I went up. Notice that I never went downward. My pencil went up and it went up. Okay, so I did not decrease. All right. And these functions, unless it were to turn back down around, and in order for it to do that, you would have needed another asymptote, you do not have a max or a min, okay? Last one, okay? We have again a fraction. This time, the fraction has an even exponent, which means that they're both going to be up top. And if there was a negative, they would just both be on the bottom. This one does not have a negative, okay? It does have a +2 grouped inside, So side to side, opposite the sign, it's going to go 2 to the left. And then that minus 1 means it's going to go 1 down. That's on the outside. And again, these are the asymptotes. Okay, so I'm going to go 1 down. And I'm going to go 2 to the left. Okay. Now, remember, this was even exponent on the fraction, and it stayed positive, so they're both on top. Very similar behavior to what happened here. Okay, oh, my drawing wasn't too even there. All right, so domain, furthest left, this arrow goes on forever to the left, so negative infinity. And it exists everywhere except at this asymptote. It approaches negative 2. And then after negative 2, approaching it, it still continues existing on to the right, always. Range. Does it always exist forever down below? The answer is no. Okay, there's nothing existing down here. So we do have a barrier at negative 1. Now, remember, asymptotes, we approach them, okay? So I'm going to put a parenthesis. And then from negative 1, it does exist forever upward. Okay? For increasing and decreasing, I'm going to put my pencil furthest to the left. And as I start drawing, I am going up, 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 up. So I go up, I increase the arrow from negative infinity up until negative 2. Now, if I put my pencil furthest left on the next section, notice that I am going downward. I'm decreasing. So, from approaching negative 2, I go downward forever. And again, increase and decreasing, we're using the x values. Max and min, do I have one? Okay, notice if I would have had, same scenario, another asymptote here, that this would have turned back up, then I would have had a min, but it doesn't. It keeps riding along this asymptote here forever. So there is no max and no min. Okay, guys? Again, this is something you should have known from Algebra 2. This was just to get a quick review in. Let me know if you have any questions.